All right, the content for chapter 11 is adaptations to endurance training. And endurance training is not just long distance running on a treadmill. There's aerobic endurance training, which is going to utilize the slow glycolysis, and there's also fast glycolysis endurance training as well. So the chapter will talk about various changes to the physiology based on endurance training. The chapter begins with the overview, and in the beginning of the chapter, we'll talk about adaptations to slow glycolysis aerobic training, then switch to a conversation about fast glycolysis training, and then the difference between high intensity interval training and other kinds of endurance training. Cardiorespiratory endurance is defined as the ability for your heart and lungs to perform long term, low intensity exercise. There are going to be improvements to this cardiorespiratory endurance via various systems through the body: the cardiovascular system, the neuromuscular system, the metabolic system. So improvements in endurance capability is a multifaceted systemic approach. With increased endurance training, there's an increased ability to utilize oxygen, and the prime measure of improved endurance training is VO2 max. That's with maximal endurance capacity, but submaximal endurance capacity is somewhat difficult to measure. It could be the case that individuals who are trained at submax endurance have lower resting heart rate than their counterparts, but more research is needed to be sure in regards to a valid measure of submax endurance capacity. Figure 11.1, that's slide 4, shows the difference between VO2 max with trained and untrained individual. Pre-training, their VO2 max starts a little bit below 20 and climbs to about 45. The cost of running, you'll notice, for pre-trained and post-training is somewhat similar, or the slope of the line. So running at 6 miles per hour is always going to cost about 19 milliliters per kilogram per minute for this particular individual. But you'll notice as they train longer and longer, the cost doesn't change. It's just that the individual is able to go to, instead of stopping at 12 miles an hour, they're able to stop at 17 miles an hour. And because of that, or one of the reasons they're able to do that is because as they train, they have an increased VO2 max capacity. You'll see now at the end of training, the VO2 max is about 55 milliliters per kilogram per minute. So the cost of running doesn't change, but they're able to go further into the bout in regards to intensity because they're able to pull more oxygen into their body. Figure 5, slide 5 is a video. I'll let you guys go through that. So major adaptations that occur to the cardiovascular system all have to do with the improved ability to distribute blood, which is oxygen and macronutrients, to the muscles. So there's going to be an increase in heart size. It used to be the case that an increase in heart size was thought to be strictly a pathological or strictly a detriment, but it seems as though that there's athlete-induced hypertrophy that allows the heart to have an increase in stroke volume. If the heart's bigger and the heart relaxes more during diastole, more blood is pulled into the heart. So there's more blood to be able to contract and get out of the heart. So there's particularly an increase in stroke volume, but there's a reduction in heart rate. So the heart doesn't want to beat. I mean, the heart wants to save as many beats as possible. So as it becomes more effective and as it becomes more aerobically trained, the tendency for the heart is to save as many heart rates as possible. If you can reduce, we did a lab in the beginning of the year that if you could reduce your heart rate by 1 beat per minute over the course of a lifetime, it's going to save millions of heartbeats, and that's beneficial for heart health. So usually cardiac output, which is a combination of stroke volume and heart rate, is going to be is going to be increased, but it's mostly because of stroke volume, and it's actually there's a reduction in heart rate. So there's an increase in overall blood flow, and that could be because of an increase in cardiac output, but it also could be an increase of blood plasma volume, which increases the overall blood volume. And that's also going to interact with increased capillary density, capillarization, and utilization of capillaries. So there's going to be more blood flow around the muscle fiber itself. Um, and with the increase in cardiac output, there's also going to be an increase in the contractilability of the heart muscle itself, particularly the left ventricle. And that's going to increase the blood pressure on the arteries and the veins, um, because the heart's pumping harder. So there are major cardiovascular changes that occur with, and particularly right now we're talking about aerobic endurance training, so long-term, low-intensity exercise. On slide 7, we take a look at the Fick equation, which says that V with a dot over it, which means the amount of, or the volume per minute of oxygen, VO2 with the dot is VO2 max per minute, or the amount of oxygen you're breathing per minute, equals SV, stroke volume times heart rate times the atrioventricular oxygen difference. So stroke volume is the amount that the heart is pulling into the, or is able to get out of actually the left ventricle. Heart rate is the number of beats per minute. And atrioventricular difference, there's a little line over the V, and we're not going to get into what that means, but the atrioventricular difference refers to the ability for the tissues to extract oxygen. So the more trained the individual and the more they're able to absorb oxygen from the blood into the tissues, the greater the O2 difference will be. It implies that there's a greater efficiency of oxygen removal and utilization for the production of ATP. All right. With increases in VO2 max, there's typically an increase in the maximum stroke volume. There's an increase in the maximum atrioventricular oxygen difference, but there's potentially a decrease in heart rate compared to age-matched controls. Heart size is going to increase, and particularly the LV, the left ventricular volume, is going to increase, and the left ventricle is the last chamber that the oxygenated blood from the lungs is going to be in before it's squeezed and pushed out into the aorta. So there's an increase in left ventricular volume, and because of that, there's a potential increase in the amount of blood that can be included in the stroke volume calculation part. So there's going to be increased pulse rate with increased aerobic training, and because of that, there's going to be cardiac hypertrophy. Just like any other muscle, the heart muscle is going to grow stronger. It's going to increase the diameter of the left ventricular wall, and that's going to allow for an increased contractilability, which is going to increase the stroke volume. There's an increase in plasma volume. So as more and more capillaries are utilized, that means that there's more volume of veins, arteries, and capillaries. And if the amount of blood, or the volume of blood stays the same, then there's going to be actually a reduction in the amount of blood that can get to the heart. Also, those little teeny venules and capillaries could potentially make it so that the blood has a difficult time coursing through such small channels. So what happens is there's an increase in blood plasma. The fluids, the interstitial fluids from the body are reduced, and they are absorbed into the blood plasma, which increases the liquidity, or it reduces the viscosity of the blood. So a couple of things, two things particularly happen. It allows blood flow in and out of the capillaries and venules to be a little bit less hampered, a little bit less, a little bit smoother, and it also increases the total plasma volume, so that with every heartbeat, there's there's more blood pumped as opposed to less. Um, the increase in blood plasma volume almost forces more blood into the left ventricle, like blowing air into a balloon will expand the balloon. Well, if there's more volume of blood and that volume of blood is being jammed into that left ventricle, then that left ventricle is going to expand because of that. That's the volume loading effect. Figure 11.2 on slide 9 shows the difference between a couple of metrics regarding the heart. So on the left it says left ventricular internal diameter, and then there's the left ventricular mass is all the way onto the right, and you'll see with runners, cyclists, and to a lesser extent strength athlete, there's increases in the left ventricular diameter and other associated um, variables that imply that the heart is growing. So with runners and cyclists, you'll see compared to the control, each one of those variables is increased significantly, but to a slightly lesser extent with the strength athletes. But it appears as though that endurance training, both aerobic and anaerobic, seem to increase the musculature of the heart. Now, it used to be the case that that an enlarged heart was deemed a pathological state. So it used to think that athlete-induced hypertrophy was not a good thing, but right now the research is suggesting that it's somewhat necessary to increase the cardiac output enough to be able to supply the oxygen and macronutrients to the working muscles and brain. Slide 9, there's an increase in stroke volume after training. Both resting and submax and max stroke volume increases. Most of the research suggests that the mechanism has a lot to do with, again, we said the increase in plasma volume. Increase in plasma volume reduces the viscosity of the blood and allows for more smooth motion of the blood throughout the body, and it increases the total volume of blood. So with each heart rate, the same amount of cardiac output can occur. The increase in blood plasma volume seems to increase the exit diastolic volume, which is going to increase the amount of blood that can be absorbed into the heart. So what happens is because the diastolic pressure drops, there creates a vacuum that pulls more blood into the heart. And if the heart is bigger and the heart can relax as much, then there's going to be a greater amount of blood pulled into the heart during diastole, which increases the preload, which is the total amount of blood that can be contracted out of the heart. But most of that increase in cardiac output is due to increases in plasma volume and contractility of the heart as opposed to the heart rate. There's actually a reduction in resting and submax heart rate with training. And the potential reason for that is because if the heart is beating less times per second, it's relaxing through diastole a little bit longer, and that could increase the amount of time that the heart has to fill during diastole. So that's going to increase the diastolic volume. It's also going to contribute to an increase in left ventricular mass because of that volume loading effect, and that's going to potentially increase the force of contraction. So most of these stroke volume adaptations are going to reduce with age. Figure 11.3, slide 10, shows the difference between stroke volume with one pre-training group compared to a post-training group, and it appears as though the stroke volume for the post-trained individuals is significantly higher. And again, that stroke volume is due to a reduction in heart rate and an increase in, that the cardiac output, therefore, would be due to an increase in stroke volume and not as much due to an increase in heart rate. Figure 11 shows the stroke volume difference for an untrained versus trained individual, and it also will show a stroke volume at rest compared to a maximum stroke volume. And you'll see again, a trained individual has a stroke volume of 90 to 110, highly trained from 90 to 110 at rest, and there's an increase in stroke volume during exercise compared to their untrained and trained counterparts. In regards to resting heart rate, there's going to be a potential decrease in heart rate with with aerobic training. In fact, there could be as much as a 1 beat per minute per week of training reduction. That could be because of increased parasympathetic and reduced sympathetic activity in the heart, especially with aerobic training. There would be more likely an increase in sympathetic activity due to resistance training, but here we're talking about aerobic training. So an increase in parasympathetic activity is going to potentially increase vasodilation of the peripheral muscles, and it's going to potentially reduce resting heart rate. And if it can reduce resting heart rate, maybe that will allow for a greater loading time, increase the preload, increase the end diastolic volume, and increase the potential stroke volume per heart rate. So there also seems to be a reduction in heart rate for submaximal efforts, and that's again potentially because there's increased enzyme activity. There could be a increase in atrioventricular oxygen difference, and an increase in potential stroke volume due to increased plasma volumes and other issues. In regards to maximum heart rate during exercise, it's 220 minus your age, or there's another reasonably similar equation, but regards to that maximum heart rate, there doesn't seem to be